structures that are most ecologically effective are also the ones that are most expensive, right? So this makes us pause and sometimes have settle for smaller structures, different types, dimensions, etc. So it relates to money. How much money do we want to spend, and what can we justify? What is considered defensible? So on one hand, yeah, you have people who say it's good for human safety, it's good for biological conservation, but I just don't want to spend that money. And I think it's ridiculous that you build these things. You might hear that as working for a DOT. But the problem is that the assumption of people who say that there's no cost if you don't do anything. And that's not true either. So rather than asking the question, how much does it cost to build this infrastructure, it's a far more interesting question to look at the balance between the costs and the benefits of what you build. Not building it versus building it. What do you spend? What do you gain? At least in theory. And we started out exploring these concepts back in 2007 with a paper that was eventually published in 2009. So on one hand, we have the cost for all our mitigation measures, and in this limited analysis was focused on reducing wildlife vehicle collisions, specifically vehicle repair costs and human injuries and fatalities. So it's quite limited. It doesn't look at, say, the value of biological conservation and threatened and endangered species, not at all. Yet it was an interesting start. So we largely focused on large ungulates, deer, elk, and moose. And what we did at the time is we summarized, well, what do we know about the costs of these collisions? It is not only vehicle repair costs, and they increase when the animal is bigger, logically. So greater cost for vehicle repair costs, the first line, when you have bigger animals. But we also have occasional human injuries and human fatalities. The probability that it happens with any specific collision is actually very small. When it happens, though, there are pretty large dollar amounts involved. So we never know which collision results in human injuries, human fatalities. So we allocated a proportion of these costs to each deer vehicle collision and elk and moose that happens. And about half of all costs with deer are associated with the occasional human injury and human fatality, even though a tiny fraction of them actually results in human injury, human fatality. But when you do your cost-benefit analysis, I think this is the proper way to deal with it. There's some other smaller cost categories included as well. So what we came up with is $6,600 for deer, $17,000 for elk, and around $30,000 for the average moose vehicle collision, based on largely vehicle repair costs and human injuries and human fatalities. We also looked at cost of mitigation measures, because that's the other part of the equation. And we did this analysis over a 75-year-long time period. This is important because, especially when you talk about wildlife crossing structures, most of the money is spent in the year that you build it. And then there's, maintenance costs, and at the end of the lifespan, removal cost. But really, you should allow that structure that costs so much to build to generate the benefits over the course of its lifetime. In the case of crossing structures, it's actually connectivity and not necessarily collision reduction, but we regard this as a package. The fences are most important for collision reduction, and they have a lifespan of 25 years. So in a 75-year long time period, you go through three sets of fences. Now, discount rate means that if you spend $1 today on building mitigation measures and you earn $1 back tomorrow by having a collision not occur, the $1 you earn back tomorrow is worth less than the $1 you spent today. So what economists say is, for intergenerational investments, meaning over 25 years, it is more appropriate to look at 1% and 3% discount rates than it is to deal with 7% discount rate that sometimes the federal government requires. So rather than choosing one, we just did the analysis for all three discount rates. Now, what is that type of information resulting? I'll walk you through this graph. This is actually data from a real road in Montana. It's Highway 83, the Seeley Swan, about an hour to the northeast of here. So on the horizontal axis, you see the mileposts, and on the vertical axis, you see dollars per kilometer per year. Let's first look at the jagged line. So based on historic data, actual carcass data collected along this road, we calculated the costs. And that is different for each mile reference post or tenth of a mile reference post. And you see that most costs are in the first 15 miles or so, and then it's generally lower. Then there's a bunch of horizontal lines in this graph. Each horizontal line represents a different mitigation measure or combination of mitigation measures. It is the economic threshold, meaning that is what it costs per kilometer per year to have that mitigation measure be in place. And if your jagged line meets or exceeds those horizontal threshold lines, it means we're basically losing more money by having collisions continue to occur than implementing that combination of mitigation measures. So you can see how this changes the discussion from, oh, that costs too much money, I don't want to spend it, to, well, actually, we have a cost that occurs when we don't do anything, and we can actually reduce our cost as a society when we implement effective mitigation measures. Maybe not everywhere. You can see there's differences between these road sections, but there's definitely a lot of road sections where we easily meet these requirements, even with a very limited analysis based on vehicle repair and human safety related parameters. So what did we do for this project? We updated the data and we also expanded. So first of all, an update. So we see each column represents different species that we estimated costs for when a collision occurs. But let's just focus on the first column, deer. You see that vehicle repair, human injuries, human fatalities are in the first couple of lines, and they add up to $14,000. And remember that in 2007, in $2,007, in the 2009 publication, this was $6,617. So we had a very substantial increase, between 2- and 3-fold when you look at all the different species. So apparently, vehicle repair costs have gone up, true, but especially the costs associated with human injuries and human fatalities. And that's all based on the value of a statistical life that transportation agencies use. And basically in this time period, it shot up from $3.4 million to $11.6, I believe. And even though there's a very small proportion of the collisions with wildlife that result in human injuries and human fatalities, because the dollar amounts have increased so much, it has a big effect on the per collision costs, right? And an expansion of the model is to include passive use values. And for that, we work with bioeconomists, and you've seen the reports over the last couple of years, John Duffield and Chris Nair. So it's basically based on what are people willing to pay to not kill the animals on the road. That's essentially what it comes down to. And even for a common species like white-tailed deer, it's about $5,000. So an update shows a steep increase in cost for direct cost parameters, and an additive cost, that's about a quarter of the total cost for passive use values. Okay, now all of a sudden, instead of $6,600, we're dealing with nearly $20,000, right? Okay, now look at grizzly bear. In size, average, we consider it similar to deer. I know that, we consider them far more compact, but many of the bears are not all that big. And if you have to make a choice, it is more like a deer or an elk. It's conservative to call it more like a deer. So the direct costs are the same. But when you look at the passive use value of an individual grizzly bear, it's like $4 million. And that gets to the point, well, maybe some species are more important than others. Adam referred to that too. It's not just about having a large variety of species. Maybe specifically grizzly bears or other threatened or endangered species might be of particular concern. And if so, now all of a sudden it might be biological conservation and economics associated with biological conservation that drive the decisions rather than parameters based on primarily human safety. Now, before we go into the cost-benefit analysis, I also asked myself a different question. As our cars change and have more technology and safety systems embedded in them, does it become safer and less risky for us to hit large mammals? Well, in fact, the answer is yes. That data for deer on top and moose down below. We first focus on the deer. This left axis shows the proportion of property damage only, and that is the solid triangles. And when there's a line between any of these symbols, it means it's significant. there's no line between the symbols. We have no significant relation and no change over time that we can detect. At the same time, the open circle, non-incapacitating human injury, a decline. So we have fewer non-incapacitating human injuries, and we have proportionally more property damage only. So there's less people getting hurt, right, over time, because presumably our vehicles have been getting safer. The same pattern is true for moose, where we have property damage only increase and non-incapacitating injuries decrease. Now, don't confuse significant with substantial, because the changes, the absolute changes in proportions are extremely small, yet they are significant. It is happening, the vehicles are getting safer, but it's not getting a lot safer, right? That is what it basically means.
You still don't want to run into them.
Correct. But this is relevant for our cost-benefit analysis, because we have seen that most of the costs are associated with occasional human injury and human fatality. We have no indication that our more modern cars are resulting in fewer human fatalities. I'm not detecting that in the graph. So when a severe accident happens, it's still deadly, right? But we do have evidence that there is fewer human injuries and a shift towards property damage only. Small, but significant. So now the second part of that equation, the cost of mitigation measures. So we try to summarize data from the field. Structures that have actually been built in certain years have the inflation correction factor applied to that, and everything is in 2020 US dollars. We know what it costs to build fences per kilometer of road on both sides of the road, $170,000 on average. I have a standard deviation. If you want a median instead, you can use that. And also a minimum and maximum, and the sample size that I have based on the sources that I was able to find. We also have costs associated with large mammal underpasses, more or less $500,000. And if you're talking about a pretty wide overpass, you're easily looking at, $4 or $5 million, or maybe 6, 7. There's a lot of variation based on how you build it and what the width of the road is and what the soil stability is and hydrological conditions, or whether you use fiber reinforced polymers. So then we calculate thresholds, right? And this is for different types and combinations of mitigation measures. How many deer, elk, or moose, or grizzly bears do we need to hit per kilometer per year for different types and combination measures to pay for themselves? Now, I only did it for fence alone, fence with a buried apron, so a dig barrier, and fence in combination with a large mammal underpass every 2 kilometers. And the last one is the same, an underpass every 2 kilometers. With every 24 kilometers, we have an overpass replacing an underpass. We focus on this one here, fences in combination with underpasses. We need to hit, it's kind of funny to talk about it that way, but 1.5 deer per kilometer per year for that combination of mitigation measures to generate more benefits than what it costs. We compare that to the value in 2007 dollars. We basically cut that in half, right? Now, mind you, we updated our values for costs with collisions, updated values for cost of mitigation measures. And essentially, it means that our thresholds have dropped substantially. And the more we learn, both the update and expansion of the model, thresholds are lower. And we learn that we should have been implementing mitigation measures more readily. That is essentially what it means. Now, when you look at grizzly bears, and we know that grizzly bears, we just heard, they need very large or wide crossing structures. Adam just referred to that. So it's important to throw in these overpasses of 50 meters wide or so. When you look at the values here, extremely low thresholds. So you need to hit only very few grizzly bears per year to make it economically defensible. And that's all largely based on the passive use value that you saw on that table, the $4 million, right? But let's bring that back to the real world. Let's bring it back very close to home. There's US Highway 93, and there is a road section where in the past and also currently, grizzly bears are being hit. Grizzly bears live in a multifunctional landscape. It's kind of surprising when you look at that landscape. But between St. Ignatius and Ronan, that is where most grizzly bears have been hit in this region. Now, this is partially mitigated with partial fences and some underpasses, some relatively small large mammal underpasses, and also a road section through the 9-pipe wetland area that has not been upgraded yet. There's an explanation for that. It basically is considered a wetland, went through its own separate environmental impact assessment, and by the time the other road sections were built, the money was essentially gone. And correct me if I'm wrong, Joe, but now we're basically gearing up towards addressing this road section as well, and it becomes relevant to figure out what do we do and how do we do it and why do we do it, because this is an important road section for grizzly bears. So it's 22 kilometers. We've had historic data between 0 and 2 most years, but in 1 year we had 6 grizzly bears hit on this road section. I think it's quite defensible and maybe even quite conservative to say, let's just assume we hit 1 grizzly bear a year on these 22 kilometers of road. That means 0.04 per kilometer per year. And the interesting thing is, this is, like 5 times higher than the economic threshold, right? And that is, throwing 1 overpass per 24 kilometers, which is coincidentally quite similar to the 22 kilometers of road that we're talking about. So, as a rough indication, you could say this is, it has become economically defensible to provide several, maybe up to 5 large crossing structures that would be suitable for grizzly bears, specifically sows and cubs, because they are more critical when it comes to their choice of crossing structure. So I think that, by showing this, an update of the model that basically already lowers the economic thresholds, an expansion of the model when we start to look at economic parameters associated with biological conservation, the trend is pretty clear, I think. The more we learn and the more we put in these models, the conclusion becomes we should have done, should have implemented, also in the future should more easily implement mitigation measures earlier, at least if your concern is it economically defensible, right? Again, we know it's good for human safety, we know it's good for biological conservation, can even make economic sense. But this model is not complete either. When you look at climate change and specifically hydrology, especially for underpasses, how big do you want to make them? What risk do you want to run of them, being washed out? Because, 100-year floods are occurring every 5 to 10 years, right? And then over the last few years, we all learned that being outdoors is important to our mental health, physical health, and especially in urban areas, suburban areas where you may have animals that are adapted to a certain level of human disturbance, and maybe not rare and maybe not all that dangerous to people. You might all consider co-use by humans. And all of a sudden you got another partnering society. In non-motorized infrastructure, we also need to get to the other side of the motorway. I live in a native neighborhood and I have to go around to get under the interstate. And if there would be a bridge there, that would be great. Of course, I don't want to invite grizzly bears into my neighborhood. So that's, but you get my point, right? So if you have strategic partnerships with other interesting society where there can be overlap in specific situations, not everywhere, not for threatened and endangered species or species that are super sensitive to human disturbance and species that might be particularly dangerous to people, you might want to separate the use. But it's yet another perspective that helps you make decisions about if we're going to build these wildlife crossing structures and what type and dimensions they should be when we are concerned about the costs.